Hello and welcome back to the Science of Concrete Materials class. This is lecture number 33 of the class. We are still on the response to stress module, and today we will talk about compressive strength. So far we have discussed the modulus of elasticity, the concept of modulus elasticity and how it's determined, the factor that's affected. And also we talked about tensile strength of concrete. Today we will talk about compressive strength. So, because compressive strength is so much greater than tensile strength, the compressive strength is widely considered to be the most important property of concrete. The method and details of testing, will be discussed and the hardened concrete properties lectures coming up in the next module. Here we will briefly mention the mode of physical response of concrete to compressive stress, the resultant stress-strain curves, and the effects of testing system properties on the response. Basically what we will be discussing. So an understanding of the nature of the physical response and the impact of testing conditions is useful in both interpreting the results of the compression or the compressive tests and understanding the behavior of concrete under load. The stress-strain behavior of concrete is normally evaluated under uniaxial compression test, in which concrete cylinder or prism is loaded along a single axis. The standard test in North America, as we will be discussing in detail later, uses a cylinder with a height to diameter ratio of about 2, loaded between rigid test platings. So due to the differences in material properties, the lateral strain due to Poisson's effects is greater for the concrete than for the end platings, resulting in friction between the test specimen and the platings, which basically places the end regions of the specimen in somewhat of a triaxial compression, as you will see in a bit. The results, this results in the formation of, conical regions at the ends of the specimen, as I will show on the next slide. Sometimes, mild lubrication of the bearing surfaces can reduce the friction so that the true tensile nature of the compressive failure is achieved. Also, in addition to lubricating the contact surfaces between the test specimen and the testing machine, other procedures have been used to help attain a true uniaxial state of stress, such as using soft platings or brush bearing platings to reduce that confinement. Another method also to increase the length to diameter ratio of the cylinder to reduce that confinement or confining effect at the ends. Anyway, we will see that in the next slides. So what we will be looking here in this lecture, the mode of cracking, the stress-strain response, under uniaxial load, the stress-strain response under confinement, the Moore rupture diagram, and we will be looking at the factors that affect the compressive strength. Okay, so if you look at this slide here, this figure here shows a schematic of a uniaxial compressive test, and it illustrates the end restraints resulting from the friction at the bearing areas at the end of the specimen. As you can see, this enlarged areas, this region here will be subjected to compression in the lateral direction, and that's actually that will impact the failure, the mode of failure of the concrete. Putting this region here in triaxial compression, and basically it results in this, barrel-shaped specimen as resulting from the end restraint. Okay. This slide here, further explains the resultant triaxial compression at the ends, and how the use of soft loading platen or intermediate layer between the end platen and the specimen will lead to a reduction in the compressive strength due to tensile stresses at the contact zone. As you can see, basically here in this case, without doing anything at the contact between these platen and the specimen, this area will be subjected, to triaxial compression, as you can see, and this will be the mode of failure. Okay, now if we reduce that friction by using, a soft material or any other means, you can see how we will get rid of that confining compression here. So the area will be actually subjected to tension, compression, rather than, compression. Okay, and that really will help. Not will help, actually will put this area in tension, compression. Will basically remove that confining compression at this zone, and it will give us a true tensile failure at the ends, rather than what happens here. Okay, so and this figure here shows the 3 different modes of failure depending on confinement. Okay, so in this figure A here, we have confinement at both ends, and you see this is the mode of failure, the cone type. And in figure B here, we have confinement at one end, okay, and no confinement at the other end, so we will end up with the basically split in failure. Okay, this figure, this figure C here, it gives us this true split in failure mode. Okay, so that's the difference when we have confinement at the ends and we don't. So let's see the physical nature of the response. As described earlier, concrete is a composite material, consisting of an essentially linear material, which is the aggregate, and a highly nonlinear material, which is the cement paste, separated by an interfacial transition zone that is, in most cases, behaves as a weak link, separating the other 2 phases. The modulus of elasticity of normal weight aggregate is significantly higher than that of the cement paste, as shown in this graph right here. Okay, so the heterogeneous nature of concrete not only affects its behavior under low stresses, as we discussed before, but in fact dominates the behavior of concrete at all levels of stress. So, as we established before, it is well known that much of the physical nature of the response of concrete in compression can be described in terms of micro cracks that can be observed at relatively low magnifications. These micro cracks, form at the paste aggregate boundary and through the mortar constituent of the concrete as compressive strain increases. Internal cracks and flaws exist, as we said before, before loads are applied. Some of these are due to segregation and bleeding, in particular beneath large pieces of aggregates or reinforcing steel. However, though, most of these microcracks are bond cracks at the interfacial transition zone, which are due not only to differences in elastic of moduli between the hardened cement paste and the aggregate, but also to different coefficients of thermal expansion and different responses to changes in moisture content, various reasons. So the incompatibility in the elastic moduli can lead to considerable stress concentrations, under differential volume changes caused by continued hydration, temperature differentials, or drying of the concrete, one of these, or all. Since the strength of the interfacial transition zone is lower than the strength of the cement-based matrix, concrete tend to form, the cracks tend to form in this region, okay? So this behavior is detailed here, as you can see, basically through a study on the progressive microcracking of concrete under load, as you can see in this figure, which I will explain. So the figure shows, the concrete behavior can be divided into 4 distinct stages. Okay? Under normal atmospheric exposure conditions, when a concrete element is subjected to drying or thermal shrinkage effects, due to the differences in their elastic moduli, differential strains are really set up between the paste, the matrix, and the coarse aggregate, causing cracks in the interfacial transition zone, as we said before. So even before the application of an external load, microcracks already exist in the interfacial transition zone between the matrix, mortar, and the coarse aggregate. The number and width of these cracks in a concrete specimen depend, among other factors, as I just mentioned now, on bleeding characteristics and the curing history of the concrete. So, as we can see here, below 30% of the ultimate load, the interfacial transition zone cracks remain stable. So the stress strain curve here remain linear, as you can see, somewhat. Okay, this is the microcracks in the interfacial zone. Okay, so as I said, above 30% of the ultimate load with increase in stress, the interfacial transition zone microcracks begin to increase in length, width, and number. Okay, this is basically going to be stage 2 right here. Okay, so the stress-strain ratio increases and the curve begins to deviate appreciably from a straight line, as you can see here. All right. Until about 50% of the ultimate stress, we will get a stable system of microcracks which appear to exist in the interfacial transition zone. This, what happened. This is basically stage 2 on the curve, and the matrix cracking is still negligible in this case, in this stage. All right. Between at around 50 to 60% of the ultimate load, the cracks begin to form in the matrix, okay, with further increase in stress level up to 75% of the ultimate load, okay. So not only does the crack system in the interfacial transition zone becomes unstable, but also the proliferation and propagation of cracks in the matrix increase, causing the stress strain curve to bend considerably toward horizontal. as you can see here. Okay. This is basically, as I said, this is stage 3, as you can see here. All right. At about 75 to 80% of the ultimate load, the rate of strain energy release seems to reach the critical level necessary for spontaneous crack growth under sustained stress, and the material basically strains to failure. Okay, as happens here. All right. So in short, basically, above 75% of the ultimate load with increasing stress, very high strains are developed, indicating that the crack system is becoming continuous due to the rapid propagation of cracks in both the matrix and the interfacial zone. This is the final stage, which is, I mentioned, number 4. Okay. This slide here further explains what was just discussed and basically relates also the cracking formation and propagation to the failure of the cylinder in compression, as you can see here. Okay. So this is basically the ascendant branch as the stress level increases, and this is, the failure, the ultimate here, and this is the falling branch, which is the crack propagation until, we reach the ultimate strain, which signifies, failure by 0.003 for the concrete and compression. This figure, if you remember, I have shown before, which is, as we discussed, and due to the heterogeneous nature of concrete, stresses are not uniform. So the localized stresses and strains are quite different from the nominal applied stresses and strains. The one we measure, for example, when we put a cylinder under compression, there will be localized intensified stresses in certain spots or certain locations that are much higher than the nominal stress and strain at failure, for example. This is shown here, this figure, as you can see, which, this is based, as I said before, on using photoelastic coatings on the surface of a concrete specimen in compression, basically to measure the localized stresses and strains. So the localized stresses, localized strains, as we can see here, maybe as much as 4.5 times the average strains. As you can see, this is the average strain right here, and the localized strains, they could reach, this is 2000 microstrain versus 460, as you can see. All right. And the localized stresses may be more than twice as high, the average stresses. As you can see here, this is the average, and this will be the localized in some locations. Okay, so the largest strains occur at the contact zone between the paste and the aggregate. Okay, this is accounting for the early formation of the bond cracks, if you remember. And this figure here, though, it shows the idealized stresses around a single aggregate particle in concrete under compressive stress. For the normal case where the particle is, the normal case I'm saying, the particle is stiffer than the matrix, okay? The aggregate is stiffer than the paste matrix. Stress analysis indicates that the following order of failure happens. First, tensile bond failure, okay, and then we have shear bond failure, then tensile matrix failure, the fourth, occasional aggregate failure. This is not the norm, occasional happens. So basically, as you can see, this is the bond failure right here. The bond is still intact in this region. Okay, the bond failure occurs here, and then we have, the tensile failure in the matrix, and then we might get failure of the aggregate occasionally. So even in compression, there will be some regions around the aggregate particle subjected to tensile stress. When the stress reaches the material tensile strength, a crack will start to grow. The compressive failure is considered is preceded by progressive cracking, largely parallel to the axis of the loading. Okay, this is the axis of the loading. Okay, so this is of course affected, as we said, considerably by the end conditions of the particle, where we test, how the testing, the conditions of the testing of the specimen, as we discussed before. Failure is eventually due, primarily to the lateral tensile stresses produced by the microstructural failure of the material. For concrete, the macroscopic level failure is distributed over a fairly wide region, principally due to the large size of coarse aggregate particles, compared to the specimens. Okay? So this is just to give you an idea of how stress develops, or how failure initiates around the aggregate particles in the concrete. Okay, so let's look at the stress strain curves. As we discussed previously, the modulus of elasticity increases with increase in strength, as shown here. So the strain corresponding to the peak compressive stress increases with increase in strength, as you can see here. Very obvious. All right. While the descending portion, look at the descending portion of the stress strain curve, becomes progressively steeper. As we increase the strength, this portion of the curve becomes steeper. Okay, so as we said before, as it should be noted that with a conventional, rather soft or low stiffness testing machine, concrete in compression will appear to fail instantaneously when the maximum load is reached, making it impossible really to record that descending branch of the stress strain curve, this part. The descending branch can be obtained, only with functionally stiff testing machines that, either one, do not store large amounts of energy, that cause the loading frame to rebound after specimen reaches the peak stress, or second, respond by reducing the load based on feedback from the test specimen, which called the closed loop testing, which is used basically to impose a specified strain rather than stress, on the history of the testing specimen. That's how we can basically catch this descending curve. All right. This is just for your information. Okay, so let's reiterate again what we have said before. The response of the cement paste and concrete, or mortar is quite different, as shown here in this curve. This is the curve for concrete at 2 different water cement ratio, and this is for the paste, the same. Okay, this figure basically, as I said, compares the stress strain curves for cement paste and for concrete. Water cement ratios, for 0.5 and 0.7 for both cases. In this case, though, stress is normalized, as you can see in the curve, and with respect to the strength, just for convenience. So the curves show that the cement paste exhibits significantly more ductility and has basically a broader high stress region than does the concrete, as you can see. Okay. The difference in the behavior between the concrete and paste, the paste constituents of the concrete are due to factors, discussed previously, if you remember, including the high stress concentrations in the vicinity of the aggregate particles. Remember that, which, basically can subject a portion of the cement paste to significantly higher stresses than the nominal stress applied to the concrete, okay, and the greater heterogeneity of the concrete, which basically results in increased transverse tensile failure. Okay, so that's really how you explain the difference, between the behavior of the paste and the concrete. We talked about this before. Okay, and finally, we must notice that, the formation of the microcracks has significant effect on the lateral and volumetric strain in concrete subjected to compression. The beginning, of the mortar microcracking corresponds to an apparent increase in Poisson's ratio. Remember, we talked about Poisson's ratio, as you can see here. Okay. So as you can see here, the rapid increase in the ratio of the strain in this direction above the strain in this direction, okay, which occurs after we reach the stress level shown right here. Okay, so this is basically at the onset of the mortar microcracking. The gross volume of the concrete in compression also begins to increase. These effects are due to the great increase in cracking that is taking place. So again, this behavior is closely related to the composite nature of concrete, since, for hardened cement paste alone in compression, the volume decreases continuously until failure occurs. Okay, so basically, as you can see, this is the direction of the loading, right? And that's the epsilon 3 basically shows the strain in the perpendicular direction. So basically, beyond a certain stress limit here, look at the increase in the volumetric strain, okay, which is, causing, an apparent increase in the Poisson's ratio, okay? This is under uniaxial loading. Okay, so in the case of biaxial loading, biaxial compression, the failure planes are the planes of maximum principal tensile strains, which are, parallel to both the applied principal compressive stresses. Such loading, causes an increase in the overall strength. All right, so the strength can increase, to as much as 27%, which occurs when the ratio of the applied stress is 1 to 0.5. So we have basically, if we have a confining stress in the other principal direction, let's say in this direction, of 50% of the stress in this direction, the compressive strength will increase by about 27%. Okay. If we have 1-to-1 ratio, the same stress in both directions, the increase in the compressive strength will be less, though, will be about maybe 16%, as I will see here. So let's talk more about the biaxial and multi-axial stress. So this figure here, look at these three figures. The figure here shows the typical stress strain curves for concrete under A, we have biaxial compression. B, we have combined tension and compression. And C, we have biaxial tension. Okay? So the test data show that the strength of concrete subjected to biaxial compression, as in figure A here, as mentioned above, may be up to 27% higher than the uniaxial strength, okay, as you can see here. So for equal compressive stresses in two principal directions, the strength increases it increases by approximately 16%, as you can see here for this 1-to-1 ratio, about less than when we have 50%. Okay. In the case of biaxial compression tension, as you can see here in this figure B, the compressive strength decreased almost linearly as the applied tensile strength increased, as you can see here. Okay. From the biaxial strength envelope of the concrete, it can be seen that the strength of concrete under biaxial tension is approximately equal to the uniaxial tension case, as you can see here. Okay, so in this case, there is no change when we have uniaxial tension or biaxial tension. Okay. So if we talk more about the lateral confinement, as you can see here, as lateral confinement increases, the effective strength and ductility of the concrete increase, as you can see, the confinement pressure. Okay, the effectiveness of the confinement is lower for higher strength concrete. You keep that in mind. Okay, so basically this is the effect of the confinement. Okay, so for the behavior of concrete under shear and stress, pure shear is not really encountered in concrete structures. However, an element may be subject to the simultaneous action of compressive, tensile, and shear and stress. So the failure analysis under multi-axial stresses is carried out from a phenomenological rather than material standpoint. Okay, so although the Coulomb-Moore theory is not exactly applicable to concrete, the Moore rupture diagram, as you can see here in this figure, back to this figure right here, offers basically a way of representing the failure under combined stress states, from which an estimate of the shear strength can be obtained. So in this figure here, the strength of concrete in pure shear is represented by the point at which the failure envelope intersects that vertical axis, which is the shear and stress, represented by the symbol tau. By this method, it has been found that the shear strength is approximately 20% of the uniaxial compressive stress. Okay, so this is a way of estimating the shear strength. Okay. Okay, so let us see here what really are the factors that affect the compressive strength. These factors were probably mentioned during the discussion of the particular topics we discussed previously, but I will reiterate them here, for completeness and thoroughness. First is the water cement ratio. So even though the strength of concrete is dependent largely on the capillary porosity or the gel space ratio of the paste, if you remember, these are not really easy quantities to measure or predict. So they are therefore not suitable for the use in the mixed design procedures, which outlined in the previous module. Fortunately, for us, the capillary porosity of a properly compacted concrete at any degree of hydration is determined by the water cement ratio, if you remember. So the paramount influence of the water cement ratio on the porosity of the hardened cement paste at a given degree of hydration is shown here on the figure to the left, which basically we discussed previously during the talk about the volume changes in the hydration lectures. Okay, as you can see here, we increase the water cement ratio. As we can see, the porosity, let me go back, I'm sorry, the porosity increases. Okay, we talked about that. So in practice, the strength of properly compacted concrete at a given age is controlled by specifying the water cement ratio. Even though the Abrams water cement ratio law, which we discussed previously, I will show on the next slide here, is not really a law, okay, in that it does not consider the degree of hydration or the air content of the concrete or the effects of the aggregate. So it's not really a law. It is, however, sufficiently correct in the usual range of water cement ratios encountered in practice, okay, to be a very useful tool for that. While, most discussions involving water cement ratio involve compressive stress, tensile strength also increases with a decrease in the water cement ratio, just for your information. So the water cement ratio law, as usually stated, is a simplification of the true state of affairs. It's not really an accurate representation. So one example of the limitation of the water cement ratio is illustrated in this figure right here. Okay, concrete that is not properly compacted will contain large voids which contribute to its porosity. So at lower water cement ratio, where full compaction is difficult to achieve, Abrams law ceases to be valid. So the point at which this occurs depends on the methods of compaction that is employed in that particular concrete. So in this regard, it might be pointed out that some sophisticated methods of compaction, usually what is used in precast operations, and the use of superplasticizers make possible the production of high-strength concrete using ordinary cement contents. So that is, if full compaction can be attained, Abrams law is obeyed even at very low water cement ratio. Okay, so as you can see here, this is the water cement ratio. As if we decrease the water cement ratio below if it is not sufficiently compacted, reducing the water cement ratio will not help much beyond a certain point. Okay, so fully compacted concrete, this is okay, but if the concrete is not fully sufficiently compacted, lowering the water cement ratio will not help, as you can see. All right, keep that in mind. So basically, this is as we talked about, the strength of concrete primarily depends on the strength of the cement paste. So the strength of the cement paste depends on the air and water content. And this, Abrams law states that assuming full compaction at a given age and normal temperature, strength of the concrete can be taken to be inversely proportional to the water cement ratio, as per this equation right here. So where, sigma sub C, which is the compressive strength at some fixed age, A is an empirical constant, B is a constant, that depends mostly on the cement properties, and water cement ratio here, which is W oversees the water cement ratio by weight. A is usually taken to be 96.5 MPa, and B, depends on the type of the cement, may be taken to be 4. Okay, this is, as I said, it's not entirely a law because it's not valid, as I said, and it has certain limitations, but it might be sufficiently valid for the ranges of water cement ratios that we use, as I just mentioned. Okay. So the second factor is age. Okay, so the rate of strength gain also depends on, as we said, on the initial water cement ratio. With low water cement ratios, mixes gain in strength more rapidly than high water cement ratio mixes, as shown here in this figure. Okay, so this is due to the fact that strength depends approximately on the cube of the capillary porosity, and because a greater portion of the cement remains unhydrated, at the low water cement ratios. So the unhydrated cement particles contribute to the initial strength gain as hydration begins, but do not really provide additional strength over time, since they represent portions of cement paste that do not really form hydration products. Okay, so there are two other practical questions that should be asked here. How can strength at different times be related to the standard 28-day strength? And second, should the strength developed after 28 days be used for design, since it is known that concrete exposed to water continues to gain strength almost indefinitely? Okay, so in practice, it is common to obtain 7 days as well as 28 days compressive strength. So it would be very useful to extrapolate a 28-day strength from 7-day or other strengths. Of course, this depends on the cement type and the current temperature. So as a general rule, the ratio of 28 to 7-day strength lies between 1.3 to 1.7, but is usually less than 1.5. Generally, the higher the rate of early strength gain over the first 3 days, the higher the ratio of the 7-day to 28-day strength. Once some experience has basically been gained for particular mixes, the ratio of strengths may prove to be useful on a particular construction project. That's something you could develop some data and develop some relation, some correlation that will help you, for example, predict certain behaviors. Okay, as we pointed out, basically previously, for high strength concrete, it's often designed for strengths at 56 or 91 days to take basically advantage of the significant increase in strength that occurs following several weeks of curing. Okay, so basically that's it's obvious. With increase in age, the degree of hydration generally increase, and the gel to space ratio increase, so the strength basically increases. Okay, so that's something it's very obvious. Next is really the cement. The effect of the Portland cement on concrete strength depends on the chemical composition and the fineness of the cement. As we discussed previously in the basically hydration lectures, the strength of the hardened cement paste comes primarily from the C3S, which is tricalcium silicate, which is basically the early strength, and from C2S, which is the later strength. And these basically effects carry through into concrete. So concrete made with higher C3S contents gains strength more rapidly, but may end up with slightly lower strengths at later ages, if you remember when we talked about the types of cements. So the relative strengths obtained with the 5 standard types of Portland cements were shown previously, if you refer back to those lectures. And although there were considerable differences in strength developments up to 1 month, at later ages, as I just said, the differences among the 5 standard types of the cements becomes really less important. So cements that hydrate more slowly, whether through changes in the composition, curing conditions, or the use of admixtures, tend to develop higher ultimate strengths. Also, the fineness, so the effect of cement fineness on strength of concrete, are also considerable, since, the rate of hydration increases with the increase in fineness, which leads to a higher rate of strength gain, as basically, stated before. So, okay. So typically the maximum particle size in cement, as we said, is about 50 microns, with about 10 to 15% of the particles less than 5 microns, and maybe about 3% less than 1 microns. So apparently, the fraction of particles that less than 3 microns diameter has greater influence on the one-day strength, while the 28-day strengths are most affected by the 3 to 30 microns fraction. Remember, we talked about cement fineness in details previously. However, even though, more finely ground cements gain strength more rapidly, very fine grinding should be avoided. Okay, because with very fine particles, excessive agglomeration may lead to local regions of high water cement ratio. On the other hand, there is evidence that particles having diameters greater than 60 microns contribute little to strength. So over the years, the trend has been toward the production of Portland cements with increased fineness, okay? But it must be recognized that, the variability inherent in cement leads to corresponding variability in concrete strength, and so requires a higher average concrete design strength. Okay, so not only do cements that are classified as the ASTM type vary considerably from plant to plant, but within a given plant, the cement characteristics vary over time. This is due to the changes in raw material, burning conditions, and the like. So it has been estimated that this variability in cement quality leads to a coefficient of variability in concrete strengths on the order of maybe 5%. So the relative effect of cement variability on concrete strength is greater, for higher strength concrete than it is for normal strength concrete. The ASTM C917, provides a method for evaluating the variability of the cement from an individual plant. So you may want to really refer to that and become familiar with it. Okay. Okay. So this is the figure here. It shows the variability or the change in strength, compressive strength, as change in the specific area, surface area of the cement measured in meters square per kilogram. As you can see here, this is, measuring at 8 hours. And one day, there's the effect is more pronounced, and 3 days, 7 days. If we go to the later ages, for example, at 1 year, the effect is not really as it is obvious for the earlier ages. Okay, so that's, you have to keep that in mind. Okay. Okay, so also mineral admixtures impact strength, as we can see. Okay, so the use of mineral admixture results in basically a modification of the structure of hardened cement paste and may result in changes within the interfacial zone. If you remember, we talked about the silica fume for its impact. So for normal strength concretes, mineral admixtures such as fly ash and blast furnace slag can be used to replace Portland cement with little effect on strength. Although, as discussed, previously in that module about mineral admixtures, the rate of the initial strength gain may be reduced while the long-term strength is increased. So the other major pozzolan, the silica fume, is generally used to increase strength and will do so even at the same water cement ratio. So silica fume not only combines the calcium hydroxide resulting from the hydration of C3S and C2S, but also fills in voids between the cement particles, reducing basically the flaw size available for crack initiation. So the combined pozzolanic and filler effects of silica fume also increase the strength and generally decrease the porosity of the interfacial transition zone as compared to that obtained in concretes without the admixture. So mineral admixtures are of great advantage in many cases, and we discussed those in details in that particular module, okay? For chemical admixtures, chemical admixtures per se have very little effect on strength of concrete, except, as they affect the water cement ratio or the porosity. For instance, air entraining agents principally affect concrete strength due to the increase in porosity, as shown here in this figure. Okay, so even in this case, however, the reduction in water content obtainable through the use of entrained air may usually result in an increase in the strength, for concretes with low cement contents, designed for constant workability. But, water-reducing admixtures, especially superplasticizers, may provide an increase in strength, even at the same water cement ratio, basically due to greater cement hydration resulting from improved dispersion of the cement particles and the elimination of the large pores that may act as internal flaws, if you remember. Okay, so chemical admixtures have their greatest effect on the rate of strength gain either by accelerating or retarding the hydration of cement. So in this connection, it is worth repeating that the observation that a decrease in the initial rate of strength gain of concrete generally leads to somewhat higher long-term strength. While an increase in the initial rate of strength gain, as obtained, with accelerators, invariably results in a decrease in the long-term strength of concrete. Okay, so you have to be aware of that. Okay. Okay, so let's look at aggregates. Although the water cement ratio is the most important factor affecting strength, the properties of the aggregate cannot be ignored, in particular in the case of tensile and fracture properties. So for normal strength concretes, the aggregate parameters that are most important are the shape, texture, maximum size of the aggregate. The aggregate strength itself is of less importance, since aggregates are generally much stronger than the cement paste, okay? So in the case of the lightweight aggregate though, or high strength concrete, aggregate strength can, play a much greater role due to the relatively high strength of the cement paste constituents of these concretes as relative to the strength of the aggregate. So that's a special case of the lightweight aggregate or the high strength concrete. But for the normal strength concretes, it's not the case. The aggregate texture depends on whether the aggregates are naturally occurring gravels, which tend, to be smooth, or crushed rocks, which tend to be rough and angular. So the surface textures, affects both bond and the stress at which the microcracks begin. If you remember, microcracks begin at the interfacial zone. So the surface texture may affect the shape of the stress strain curve but has little effect on the compressive strength of the concrete. All right, so that's something to keep in mind. At low water cement ratios, crushed rock will lead to higher concrete strength because of better mechanical bonds, but this effect disappears as the water cement ratio increases. However, though, if mixes are considered on the basis of equal workabilities, listen to this, equal workabilities, this difference becomes unimportant because the lower water requirements, for smooth aggregates, lowers the water cement ratio of the paste, which offset the effect of the lower bond. All right. The use of maximum size aggregates affects the strength in several ways. Under compressive loads, the larger aggregate particles tend to cause a greater stress concentration and a resulting reduction in compressive strength. Also, larger aggregate particles provide more restraints to volume changes in the paste and so may induce additional stresses in the paste. So you have to be aware of all these variables. Which basically in this case may weaken the concrete. So the effect of the maximum aggregate size on the strength of the concrete at 3 water cement ratios is shown actually here in this figure. Okay, for the mixes shown in the figure here, concrete workability increases as coarse aggregate size is increased. Okay, so the negative effect of the increased coarse aggregate size on strength are basically offset. However, if the mixed water is decreased at a constant cement content. Okay, the concretes made with larger aggregates tend to exhibit more variability, probably due to some tendency towards segregation. Okay, so study this graph very well. The next factor is basically we have the interfacial transition zone. As we discussed earlier, the strength of the interfacial transition zone has a small but measurable effect on the compressive strength of concrete and a major effect on the tensile and fracture properties, as we have shown before. Okay, so major changes in the strength of the interfacial zone can affect the compressive strength on the order of maybe 10 to 15%. But, as discussed before, variations in the strength of the interfacial transition zone may affect the tensile strength on the order maybe of 40%. Okay? So the increase in the aggregate roughness and the strength of the interfacial zone tend to have, similar effect on the strength of the concrete. Okay, so that you keep that in mind. And you remember, we said many things we can do, like the use of silica fume and the selection of aggregates in order to have or to improve the strength of the interfacial zone. Okay, the last factor I'm going to discuss is really the rate of loading, which also impact the strength of the concrete. So both tensile and compressive strength of concrete increase as the rate of loading increases. Okay, so the stress or the strain rate sensitivity of concrete is closely tied to the degree of saturation. With dry concrete showing much less sensitivity than wet concretes. Okay, so this is really what I'm going to talk about, the rate of loading. We will visit this topic again when we talk about the testing of hardened concrete. Okay, so basically this is the end of lecture 33, and this is the end of the response to the concrete response to stresses module. Next time we will start on the next module, which is the testing of hardened concrete. So until then, thank you for watching, and I will see you next time. Thank you.